Okay, these are the notes for Unit 5, Day 2, and they start. And today what we're going to talk about is the extreme value theorem and something called global and versus local. Those are two terms we're going to use today or learn today, and also critical points. The essential question is, what are extreme values, and how do we locate critical points? So let's talk about what the extreme value theorem says. So this is a third of these big three theorems that we have in differentiation. We learned about the intermediate value theorem, and that was at the end of Unit 1, I believe. And then just yesterday, we learned about the mean value theorem. And now we have the extreme value theorem. So the extreme value theorem says this. If we have a function f and it's continuous on a closed interval, so a, b, so closed interval, these are the closed interval brackets a to b, then the function has both a maximum value and a minimum value on the interval. So if you think about it, we've talked a lot about making sure the hypothesis is true in order to use the conclusion. This is another one of those situations where the hypothesis of the extreme value theorem is that we have a function f that is continuous on the closed interval. Okay, so in other words, you can't have any holes, you can't have any jumps, you can't have any asymptotes. Okay, it's got to be continuous. You got to be able to draw it from A to B without lifting your pencil. Okay, so basically it's saying then this: if we go from A to B and draw that function out with your pencil, then that function is going to have a maximum somewhere and it's going to have a minimum somewhere. So it's going to have a biggest value, f of d in this case, and it's going to have a littlest value, f of c. Okay, and that's a guarantee. Again, the hypothesis has to be true. It's got to be continuous on that closed interval. Okay, in other words, we got to have these endpoints here, and then we can have a big and a little value on the interval, and those can occur anywhere on that closed interval. So what we're basically saying is that all values for the function are going to fall between that littlest and that biggest value. Okay, so let's talk about these two terms, global versus local. Whenever we talk about minimums and maximums, we generically call those extreme or extreme values. Okay, extreme being like way away from the middle, so to speak. So we have extreme, and maximums and minimums are extreme because they're at the ends of the spectrums, so to speak. Global, or in other words, absolute. Global maximum is the largest function over the entire domain. So I call this the biggest of the big. So it's the highest function value in this entire domain. Okay, local maximum would be like the largest function value in a certain vicinity. So for instance, this would be a local maximum right here at about x equals 2. It certainly is the biggest in its neighborhood, in its area, but it's not the biggest of the big. Okay, so that's global versus local. And again, global, another word for global is absolute. Another word for local is relative. I should have that in there. And the same can be said about minimums. We have a global minimum, that's f of c down here. And this valley right here that looks to be at about maybe an x value of -0.5, that would be a local minimum because it's the smallest value in this little area or in this little neighborhood. Okay. So when we talk about global versus local, we say global or absolute maximums. F of c is an absolute maximum value of f of x, if and only if f of c is greater than or equal to all other values f of x. Okay, and then the opposite of that would be an absolute minimum. So if you notice, the only thing that's changing is the sign here, and instead of max, it says min. Okay, an absolute minimum is, f of c is a minimum value of f of x if and only if f of c is less than or equal to all other values in the function over that domain. And then locals, and again, another word for local is relative. So we'll talk about the synonyms in just a second. But a local maximum would be if we have a big value in a reasonable region. Okay, so it doesn't have to be over the entire domain, but it's in the neighborhood, so to speak, on either side of where that location is. And same with a relative minimum, it would be the smallest value in that little region or neighborhood, so to speak. So let's talk a little bit about the synonyms I'm using, because they can be kind of confusing from time to time. Global means over the entire domain. Okay, another word for global is absolute. Okay, biggest of the big, littlest of the littlest. Local is not over the entire domain. It's just in a specific sub-region. We like to call it a neighborhood. And the synonym for local is also relative. So we use local and relative, those two terms interchangeably, which is why I'm kind of mixing them up in this chart here. So, for instance, we might think about a global, we have the highest mountain on Earth would be a global maximum, or we could talk about the highest mountain in Colorado, which would be a local maximum. Okay, so we're kind of switching gears here. Now we're going to talk about critical points, and critical points kind of tie in. The definition of critical points are locations on a function graph at which the derivative is either 0 or undefined. So think about derivative is a tangent line. The slope of that tangent line is 0, which means it's horizontal, or it's undefined, which means it's vertical. Okay, they're important, which is why we call them critical points, because the relative extrema can occur at those points. So think about the derivative being equal to 0, meaning that the derivative is horizontal tangent. We're going to find those at hills and valleys. Okay, so these critical points are going to be used to locate relative extrema, and they occur at those critical points. Sometimes those extrema might be absolute, but they don't have to be. And we'll get into when they're absolute and when they're relative in a different section. Okay, let's look at some examples. So let's go ahead and stop the video, but you're going to look at these two functions, and you're going to classify locations as either global maxes or global mins, local maxes or local mins, and you're going to classify them as to whether or not they're critical points. Okay, so why don't you stop the video at that time, and in your notes try to identify and mark those locations with A, B, C, D, and E. Okay, so I'm assuming you've attempted this on your own. So let's talk about global maximums. So here's your global max on this function, this purple function. It's the biggest of the big. Okay, your global min is going to be the littlest of the little, and it happens to be the left endpoint right here. Okay, so there's only one global max and there's only one global min on the closed interval, and that'll be true for any case. But we can have several local maxes and minimums. Okay, a local max is going to be the top of any hill. A local min is going to be the bottom of any valley. So we've got a local max here, and we've got a local min there. Okay. And we've also got a local min at this right endpoint. This right endpoint is a smaller value than anything that's adjacent to it. So that the endpoints will always be either local mins or local maxes. And sometimes they're even globals, like in this case, this left endpoint. Okay, so now the critical points. So the critical points are anywhere where we can draw either a horizontal tangent or we can draw a vertical tangent. So when we're looking at this, we can draw a horizontal tangent whenever we have a hill or a valley. So this is not only a local min, but it's a critical point. And this is a local min. Excuse me, it's not a local min. This is a critical point. This curve flattens out here. And so it has a tangent line that's horizontal, so it has a zero derivative. But if you notice, this location is not a max or a min. So it's not a C or a D, it's just a critical point. But it's not the location of an extrema. And we have a specific term for this. We call it a plateau, where it flattens. So this is kind of increasing, and then it's flattening, then it's increasing again. Okay. And then we also have a critical point here at this global max. Again, we have a horizontal tangent. And then we also have a critical point here at this local max. Again, another horizontal tangent. So those are all the criteria for this function. Now let's take a look at this function. So let's go back to here. Let's find the global max. So the biggest of the big is way up here at the top. Our global max is right there at the top of that hill. Our global min, the littlest of the little, is going to be down here. That's the smallest function value. Now let's talk about local maxes and local mins. So here's a local max at the left endpoint. All the values adjacent to it are tinier. Here's a local max at the right endpoint, because again, all of the values adjacent to it are smaller. And then we have a local min down here at this cusp, where everything in its vicinity is larger than that bottom of the cusp value. Okay, now let's talk about critical points. So critical points, again, are going to be anywhere where we can draw a horizontal tangent. And we can only draw a horizontal tangent right here at the top of this hill. We only have a hill. We don't have any valleys, and we don't have any plateaus. So we only have one critical point over this closed interval, and it's right here at the absolute max. Okay. As far as the cusps go, we know that cusps are points of non-differentiability. Okay. So that means that this cusp here has an undefined derivative, right? We've got two different curvatures coming together here at a sharp pointy point, for lack of a better word. And so that, since the derivative is undefined there, that is also a critical point. And likewise over here, the derivative is undefined here at that cusp, so it is also a critical point. Okay, so let's move on to these and try these examples. It says not all functions have maximums or minimums. So consider these functions. They're all over the closed interval 0 to 6. This one is just tiny. You can't see it, but that's 0, or not 0 to 6. This one is 1, 2, 3, 4, -4, 2, 3, 4, 5, 6, 7. This is -4 to 7. So I lied about that. They're not all over 0 to 6, but each of them has a closed interval. And ask yourself, is the function continuous? Does it have an absolute max? And does it have an absolute min? Okay, so go ahead and stop the video and try these three on your own. Okay, I'm assuming you paused the video and tried them on your own. So let's take a look at this first one. This is a linear function, but it has open endpoints on the left and open endpoint on the right. So is the function continuous on the closed interval from 0 to 6? That answer is no. It's not. Does it have an absolute maximum? And that answer is also no. This is not an absolute maximum because it's not defined. So this is not a filled-in endpoint. And so we can keep getting closer and closer to it, but we can't attain a maximum value. And then does it have an absolute minimum? For the same reason, it doesn't have an absolute minimum. Okay, so this function has none of these criteria. Let's take a look at this function. Is it continuous on 0 to 6? And the answer is no, it's not. We have an asymptote right here, and we know that that's a point of discontinuity, which means we've got to lift our pencil to jump over that asymptote. Does it have an absolute maximum? That answer is no. Both of these parts of the curve are going up indefinitely, so they're going up to infinity. So it doesn't have an absolute maximum. Does it have an absolute minimum? That answer is yes. Remember, we're on the closed interval of 0 to 6. We're not going to extend these out forever in either direction. They might look asymptotic if we did, but we literally stopped them here and here. And since when we get to 6, it's a closed interval, so we know we're including this endpoint here. We know that this is the smallest function value on this closed interval. So it has a minimum and it's right here. And it's just slightly bigger than 0. Okay, let's take a look at this one. So is the function continuous? Not on 0 to 6, the domain's different here. The domain is actually -4 to 7, I think. The answer is no, though, because we have the asymptote. Does it have an absolute maximum? That answer is also no, because this goes up indefinitely, which means it goes up to infinity. And does it have an absolute minimum? That is also no, because it goes down to negative infinity. So this function has neither a maximum nor a minimum. So those are some of the examples that you see where they may or may not have a maximum or a minimum in absolute. Okay, so I mentioned it a little earlier, the 3 value theorems that we've covered so far this year. Okay, so here they are. We know what the intermediate value theorem, the mean value theorem, and the extreme value theorem have in common. So all 3 of these theorems guarantee the existence of a function input that has a certain property. Okay, so we're really going to kind of practice these. And I've talked a lot about making sure that the hypothesis is true in order for you to use the conclusion. And so that's getting into doing a lot of justifying of problems. So any AP problem that asks you about the existence of a function input with a certain property is almost certainly asking you to apply one of these theorems, either the intermediate value theorem. Remember, the intermediate value theorem was if I have 2 function values, a small and a large, and I pick a function value in between, then I've got to have an x value in the domain. The mean value theorem is that our average rate change and our instant radius change are equal if and only if we have a continuous and differentiable function. And then what we're talking about now, the extreme value theorem. Okay, so we have a function input with a certain property. Okay, and all 3 of those theorems are following that sort of idea. Okay, let's take a look at this problem here. So let f be a function with the selected values given in the table. So here's function f. We've got these selected values. It says which of the following statements must be true. Okay, so here are these 3 big theorems again. So by the intermediate value theorem, there is a value c in the interval from 0 to 3, the domain, such that f of c is 2. Well, 2 is certainly in between 0 and 6. So you might want to consider that to be true. Okay, but in order for that to be true, we have to have a continuous function. And does it state up here that our function is continuous? And the answer is no, it doesn't state that the function is continuous. So this might occur, and it looks like it does, but it doesn't have to occur. So we could have some sort of discontinuity here that skips over 2 because we didn't state that the function had to be continuous. So just by noticing that we didn't say it was continuous, then we can knock out 1 and 3 because 1 and 3 need continuity. We can also knock off 2 because 2 needs continuity and differentiability. So just to kind of review these 3 theorems, the intermediate value theorem says if f is continuous on a closed interval, okay, the mean value theorem, f needs to be continuous on closed interval and differentiable on the open interval. And the extreme value theorem says that f needs to be continuous on the closed interval. So these are the hypotheses for all 3 of these theorems. And if you notice, we never say this is continuous. Okay, so the answer to this is none. None of these must be true. They might be true. But in order for them to must be true, we have to meet these hypothesis criteria first, and we don't. Okay, let's talk a little bit about critical points. A point of a function on a function of graph f at which the derivative equals 0 or the derivative does not exist is a critical point. Okay, so we can do this mathematically. This is very mathematical. We're going to get the derivative in factored form. Okay, and that's going to be the easiest to determine whether or not where the locations are that are 0. And so we're going to take that derivative, set it equal to 0, and solve the values of x. And those are going to be our critical points. Then we have to take a look at the function and examine it for values that make the derivative non-existent. Okay, undefined, so to speak. And so this is going to be particularly pertinent when we have a derivative that's a ratio, a fraction, right? And so we might have a denominator that we have to consider, which would make the derivative undefined if it was 0. And then we need to summarize our information. So we need to take a look at these two scenarios, 2 and 3, and summarize all of that in a statement. Okay, so let's take a look at question number 2. Question number 2 is a calculator question. And so we're going to use our calculator to evaluate this derivative. Notice that I've given you the derivative here. There's no need for you to differentiate. So we don't need to differentiate to get f prime. It says how many critical values does f have on the open limit interval from 0 to 10? So we know that we need to look for where the derivative is 0 and where the derivative doesn't exist. So we're going to graph this. Okay. And so when we graph this, remember to be in radian mode because we have a trig function here. When we graph this, we're going to set up specifically our window to go from 0 to 10 for our x values. That way we're looking at the appropriate domain and we don't have anything else to distract us. Okay, so I put this into my y1. I'm in radian mode, and I get something that looks like this. Notice I go from 0 to 10, nothing to distract us. Now, since this is the derivative, I need to look for where it's equal to 0 or where it's undefined. Okay, and this is an open interval, so I'm not including 0 and I'm not including 10. Now, I can't really see a whole lot here because this y-axis doesn't have enough resolution to it. So I'm going to zoom in here. Okay. And so I zoomed in, and now I can start to see that it is crossing the x-axis. I'm going to zoom in even more. So my axis from 0 to 10, my domain, my range is from -2 to +1. So now I can see I cross here, and here, and here, and then all of this dips below. So these 3 locations are where the derivative is equal to 0. So we have 3 locations. We have no locations where it's undefined. So where there's any gaps in the values. So we have 3 critical points. Okay, so starting in class, we'll go over the takeaways from the notes, and then we'll go and do the last few examples as a class.